Good evening, everyone. Today we are going to discuss about Euclid's division algorithm and problems regarding Euclid's division algorithm. First of all, let us revise Euclid's division algorithm. Euclid's division algorithm states that if there are two positive integers a and b, then there exists q and r, unit pair of integers q and r, such that a is equals to bq plus where r is 0 is less than or r is less than b. This is what Euclid's division algorithm. That is, dividend is equals to divisor into quotient plus remainder. By using this, we have found out HCF of two or more numbers. By using Euclid's division algorithm, we can find out general form of the numbers also, which we have discussed in the first class and second classes. That is, by showing how 2n plus 1 is odd and 2n is even. Today we are going to discuss some problems regarding Euclid's division algorithm. First one, by using Euclid's division algorithm, show that any positive odd integer is of the form of 6q plus 1 or 6q plus 3 or 6q plus 5. So we have to show that the odd positive integers are in the form of 6q plus 1, 6q plus 3 and 6q plus 5. Let us take a as a number a, b, any positive integer such that a is equals to, here 6 is our divisor, q is our quotient and 1 remainder. Here 3 is remainder and 5 is remainder. In the first class we have discussed, if there is any divisor, then the remainder should be less than this divisor and greater than or equals to 0. That is 0, 1, 2, 3, 4, 5. That is 5 is less than 6, 4 is less than 6, 3 is less than 6, 2 is less than 6, 1 is less than 6 and 0 is less than 6. The remainder should be less than the divisor and it should be greater than or equals to 0. So 0, 1, 2, 3, 4, 5 are our possible remainders when we are considering 6 as the divisor. Now, if 0 is the remainder, then we have to consider 6q plus 6. This is first positive integer. If 1 is the remainder, a is equals to 6q plus 1. 2, that is 6q plus 2. 6q plus 3, 6q plus 4, 6q plus 5. Other than that, we can't go further, because if you go further, that should be 6q plus 6. The remainder can't be greater than or equals to 6. That should be always less than the divisor. So that should be less than 6. That is 5, 4, 3, 2, 1, 0, and that should not be negative. So 0, 1, 2, 3, 4, 5, and we got here 0, 1, 2, 3, 4. So we have taken 6 numbers here, that is a is equals 6q, a is equals 6q plus 1, a is equals 6q plus 2, a is equals 6q plus 3, a is equals 6q plus 4, a is equals 6q plus 5. So he has asked us to show that the positive odd integer should be in the form of 6q plus 1, 6q plus 3 or 6q plus 5. In this we have to show that this is odd integer and this is odd integer and this is odd integer. How can we show that these are the positive odd integers or odd integers? By taking the general form of odd number. The general form of odd number is 2n plus 1. 2n plus 1. So if you are considering any of these numbers, have to show that this number should be in the form of 2n plus 1. Then only we can say that these numbers are odd integers or odd positive integers. Let us see. How can you say that the general form of odd number should be 2n plus 1? Because whenever you divide an odd number by 2, then the remainder is 1. The remainder should be 1. Suppose if you go for 3, 2 ones are here, the remainder is 1. 2 into 1 plus 1, that is 3. If you go for 5, 2 into 2, again you got the remainder as 1. Here this should be any national, that is 2n. N is nothing but whatever quotient you are getting when you are dividing the odd number by 2. So 2n plus 1 is the general form of the odd integer. So now we shall go for first case, that is a is equals to 6 cube plus 0. Case 1, a is equals to 6q plus 0, that is a is equals to 6q. We have to see whether this can be written in the form of 2n plus 1. Let us see that. You have to take 2 common, that will be 3q. Is there plus 1 here? No, there is no plus 1. So this is in the form of 2 into 3q, that is, let us take 3q as p, 2p. Then you are dividing the number by 2 and you are getting the remainder as 0. So this is not odd integer. So this should be even integer. In the first case, this is not odd integer. So a is equals to p is an even integer. Therefore, a is equals to 6q is not positive odd integer. A is equals to 2p is an even integer. This is our first case. If you go for second case, let us. Second case is 6q plus 3q. Can you take 2 from 1? No, we can't take 2 common from 1. So we can't take 2 common from 1. So it is remain as it is. That is 2 into 3q plus 1. That is, let us take 3q as p. That is 2p plus 1. This is in the form of 2n plus 1, which is just odd integer. So 2p plus 1 is an odd integer. So is an odd integer. Therefore, 6q plus 1 is an odd integer. This is our second case. If you go for third case, then again that will be 6q plus 2. This is how we have to take, because if a is equals to bq plus r is Euclid's division algorithm, we have to take this part of the Euclid's division algorithm from this. So that can be q is quotient, r is remainder, which we are considering as 0 to 5, as 6 is our divisor. So a is equal to 6q plus 2. This is our third case. A is equal to 6q plus 2. Now let us take 2 common, because we have to divide a number by 2, whether it is odd number or even number. We have to see whether it is odd number or even number. We have to divide the number by 2. So let us take 2 common. Then you will get 3q plus 1. This will be your whole quotient, 3q plus 1. Here plus 1 is not there. Here 2 into 3q plus 1, it is multiplied by 2. So that is not separated from this entity. So 2 into 3q plus 1 is nothing but 2p. Again, let us take 3q plus 1 as p. So 2p is an even number, because general form of even number is 2n. That is even integer. A is equals to p is an even integer. So 6q plus 2 is an even integer. This is not odd. Now we have to go for fourth case. Like this, we have to see for 6 cases, so that we can show that the positive odd integer will be in the form of 6q plus 1 or 6q plus 3 or 6q plus 5. You have to remember that whichever is the divisor here, you have to do that many cases here. That is, if 6 is divisor, then you will get 6 cases. If 7 is divisor, then you will get 7 cases. Now, as 6 is divisor, you will get 6 cases. This is our fourth case. That is, A is equals to 6 cube plus 3. 6 cube plus 3. This can be written as 6 cube plus 2 plus 1. I am dividing 3 as 2 plus 1 because if you are dividing this number by 2, that will be 3 cube plus 1 and you will get plus 1 separately. This plus 1 will be remained here. So 2 into 3 cube plus 1 plus 1. That is 2p plus 1, which is odd integer, which is an odd integer. This is nothing but if you are going for division of 6 cube plus 3, that is 2 3s are 6 plus 1s are, you will get 1 as remainder. That's why 2 into 3 cube plus 1 plus 1 is the remainder. 2 into 3 cube plus 1 is the quotient plus 1 is the remainder. So that is 2p plus 1, which is odd integer. This is odd integer because the general form of odd number is 2n plus 1. So A is equals to p plus 1 is an odd integer. 6 cube plus 3 is an odd integer. Now let us go for fifth and sixth cases. I hope everyone is following the class and everyone is understanding. If you have any doubts, you can post here in the comment section so that I can attend your doubts. Now, fifth case is A is equals to 6 plus 4. Again, you have to take 2 common, that is dividing this whole equation by 2, that is 2 into 3 cube plus 2, which is 2p. 3 cube plus 2 can be considered as p. So 2p, which is an even integer. That is 6 cube plus 4 is an even integer. Next, going for sixth case. That will be 6 cube plus 5, and we will be getting here if you are taking this as 6 cube plus 5, then that will be 6 cube plus 4 plus 1. I am making this as even and I am dividing that with 2 and will be remain with 1 as remainder. So 2 into 3 cube plus 2 plus 1. So this is in the form of 2p plus 1, which is general form of odd integer. A is equals to p plus 1 is an odd integer. So 6 cube plus 5 is an odd integer. From cases 2, 4 and 6, you can say that any positive integer will be in the form of any positive integer will be in the form of 6 cube plus 1 or 6 cube plus 3 or 6 cube plus 5, hence by using Euclid's division algorithm. This is how we will be proving whatever the general forms are given. So just remember that I said that the general form of odd integer is 2n plus 1 for odd numbers. If the divisor is 6, then the remainder should be 1, 3, 5. You can check this by taking some examples. Let us take some examples for odd numbers which are greater than 6 so that it will be very easy for us to see. Let us take 7, 9, 11, 13, 15 and let us divide these numbers by 6. Then let us see what are the remainders you are getting. 6 1 are 6. 1, that is 6. Let us take this as cube plus remainder as 1. Next, if you are going for 9 divided by 6, that is 6. Q is quotient plus remainder is 3. If you go for 11, 6 1 are 6, remainder is 5, 6 cube plus 5. If you go for 13, that is 6 2s are 12. Again you are getting 1 as remainder, that is 6 cube plus 15, 6 2s 12. You got 3 as remainder, that will be 6 cube plus. If you go for 17, 6 2s 12, that is 5, 6 cube plus. That means whenever the divisor is 6, then you are getting the remainders as 1, 3, 5. If you are dividing that by, dividing odd number by 6, then you will get 1, 3, 5 as the. So whenever you are given the divisors are changing, this general forms will be changed. This general forms will be changed with regarding to the divisors. Let us see another problem, so that it will be very easy for you to understand. By using Euclid's division lemma, show that square of any positive integer is of the form 3p or 3p plus 3p or 3p plus. Let us take a, b any positive integers, and here 3 is given as divisor. 3 is given as divisor. Then what should be our remainders? 0, 1. We can't go beyond that because the remainder should be always less than the divisor, and that should be greater than or equals to 0. So 1, 2 are the possible remainders whenever the 3 is our divisor. So you have to take a equals 3q plus 0, 3q plus 1, and a equals to 3q plus. Now he has asked us to show that square of this positive integer should be in the form of 3p or 3p plus 1. Let us take the square of this, that is squaring on both sides, that is a square 3q whole square. A square 3q whole square, that is 3 square into q square, that is 9q square, that is a square is equals to, let us take 3 common because we are asked that to show the square of the integer should be 3p or 3p plus 1. So 3 into this is 3q square. Let us take 3q square as p, is square of the positive integer is of the form 3p here. Square of the positive integer a is 3p. Let us go for next one, that is again we have to square it because we are asked square of the positive integer. So squaring on both sides. This is our second case, this is our first case, and this is our second case, that is a square is equals 3q plus 1 whole square. This is in the form of a plus b whole square. So apply that formula here, a square plus 2ab plus b square, that is a square plus 2ab plus b square, that is 9q square plus 6q plus 1. 3q square, 3q whole square is 9q square plus 2 3s are 6q. 6q into 1 is 6q plus 1 square is 1. 9q square plus 6q plus 1. Here you have to take 3 common again, that is 3q square plus 2q. You are remained with plus 1 because you can't take 3 common from plus 1. That will be 3p plus 1. So square of the positive odd integer is of the form 3p plus 1. Next let us go for third case, that is a is equals to 3q plus 2. Again squaring on both sides, that is a square is equals to 3q plus 2 whole square, that's in the form of a plus b whole square again, that is a square is equals to a square plus 2ab, that is 2 into 3q into, sorry, I will write it reducing this so that it will be easy for you to understand. A is equals to 3q plus 2 squaring on both sides, that is a square 3q plus 2 whole square, that is a square is 3q whole square plus 2 into ab, that is 3q into 2 plus b square is 2 square, that is 9q square plus 2 3 are 6, 2 are 12, q plus 2 square is 4. Again you can take 4 as 3 plus 1, so that From this you can take 3 as common, that is 3q square plus 4q plus 1 plus 1, that is 3p plus. From 3 cases you can say that square of the positive integer will be of the form 3p or 3p plus 1. 3p or 3p plus 1. In first case we got 3p, in second case and third case we got 3p plus 1. So we can say that square of any positive integer will be of the form 3p or 3p plus 1. So let us see by taking some examples. Let us take some positive integers 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Square of 1 is 1. Square of 2 is 4. Square of 3 is 9. Square of 4 is 16. Square of 5 is 25. Square of 6 is 36. Square of 7 is 49. Now, the divisor should be 3. The divisor should be 3. That means this square should be divided by 3. That is 3 into 3 zeros are 0 because you can't divide 1 by 3. So 3 zeros are 0. The remainder is 1. 3 into 0 plus 1. If you go for 4, that is 3 ones, 3, 3. 1 plus 1. Again, go for 25. 3 into 8 plus 1. 36, 3 12s, 49. 3 16s plus. So if you see here the general, then this will be again this is 3p plus 1, 3p plus 1, 3p, 3p plus 1, so on. You can say that square of the positive integers, of the form 3p plus 1 on 3. This is how we can show that square of the positive odd integer is of the form 3p or 3p plus 1 by using Euclid's division algorithm. I hope everyone have understood this concept and these problems. If you have any doubts, you can ping me on WhatsApp so that I can solve those problems for you. Bye everyone.